Okay, so in this section here, we're looking at probabilities using combinations. So we're going to combine those two pieces of knowledge. We're just going to look at some example problems. We're familiar with probability. So we're going to look for probability. In this case here, we have Lotto 649 has participants picking 6 numbers between 1 and 49. So that's the name, 649. We were picking 6 out of 49. So this is the old lottery in Ontario. I think it's been replaced by Lotto Max and I believe some other ones out there now. But this was our old Ontario lottery. You got your grand prize if you had your 6 numbers matching the randomly drawn 6 numbers, regardless of their order. And so the probability of winning that grand prize is the probability of event A equal to the number of desired outcomes over the number of total possible outcomes, the entire sample set. So we need to pick the 6 matching numbers. Well, how many? If there's 6 numbers they draw, it's just those 6 numbers. So there's only one way to win. You have to match all 6. Mathematically, we have 6 numbers to choose from, and we have to choose all 6. Okay, we could just put a 1 there, but this will help out with the next part. Now, there's 49 numbers in the total draw. Whatever they use, a drum or whatever to draw these numbers, and randomly chosen are 6. So 49 choose 6 is our total possible outcomes. So 6 choose 6 is 1 over, and then our total number of outcomes works out to 13,983,816. So the odds of winning the lottery are pretty slim. Percentage-wise, it works out to approximately 0.00007%. Or sorry, not percent. 0.00007. So let's knock off 2 zeros, move that over. 0.00007. So pretty slim chances of winning the grand prize in terms of an individual ticket. Now, what if we say, okay, well, maybe we don't get the grand prize, but maybe we get one of their secondary prizes where instead of getting all 6 numbers, we get 5. And I believe 4 and 5 matching numbers, even maybe 3 got you, a 3 got you a free ticket or something, 4 got you some money, 5 got you a little bit of money. So what if that was the case and we want to just match 5 of the 6 numbers? Well, the probability of our event A is the number of desired outcomes again over the number of items in the sample space. So this time, there's 6 winning numbers. We just want to pick 5 of them. So we're going to do 6, choose 5. 6 numbers, let's choose the 5 winning numbers that we will have on our card. And then we have to pick one more number. It can't be the winning number. So it can't be the 6th number. So out of the 49 numbers available, we've taken up 5 of the winning numbers plus the one we didn't pick. So now there's 43 more numbers available. So it's 43 because 49 minus the 6 winning numbers. So that picks our last number because it can't be one of the 5 winning numbers or the 6 winning number that we didn't pick. And again, our sample space in total is 49, choose 6. And so we get 6, choose 5 times 43, which is going to be 258. So 6 choose 5 is 6 times 43 is 258 out of 13,983,816. Your chances are still pretty slim. If we divide that out to get our decimal and then percent, we get 0.0018% chance of winning. So you're still much smaller than 1% chance of winning. Now, that being said, A similar type of odds lottery in New Jersey once had about 50 people win the grand prize at one time. So it can happen that the probability might be slim, but it is possible. They all picked their winning lottery ticket numbers off of their fortune cookie. They all had the same fortune cookie and it had the same winning numbers. Okay, one more problem to take a look at here. We have an employee work group is being made of 10 people. Members are being selected from the 12 paint department employees and 15 weld department employees. So 15 people in the weld department, 12 people in the paint department. We're picking out 10 people from those groups of employees. What is the probability that at least 8 weld department employees are selected? So in this case, again, we have our same type of setup. We have the probability of event A equals the number of desired outcomes over the number of items in the sample space. And so we want to pick at least 8 weld department employees. So to ensure that we pick or select our 8 weld department employees, we have 15 to select from. We want to choose 8 of them. So 15 choose 8, we'll select our 8 weld department employees times the remaining employees. So once we've picked 8 weld department employees, we're left with 7 weld department employees, 12 paint department employees to pick the remaining people. So this guarantees at least 8 weld department employees. We can pick more though. So we have 7 more weld department and 12, so that's a total of 19. Choose 2. So pick the 8 people for sure out of the weld department, and then the rest don't matter. Now we divide that by the total number of outcomes, which means there's no restrictions. We're just taking the total number of people, 12 plus 15, and choosing 10. So 12 plus 15 gives us 27. Choose 10. And then we calculate that all out. So we get 15. Choose 8 times 19. Choose 2. And that's going to give us 1,100,385. So 100,385. Divided that by 27. Choose 10. That is 8436285. So a total of 8,436,285. And if we divide those, we get 13% approximately. So there's a 13% chance that there'll be at least 8 weld department employees. And in the past, we've had the question of when should I use percent, when should I use fraction, when should I use decimal with probability. In these cases here, because there's so many decimals, the percent is okay to show that it's a really slim percent. This here, the fraction, I mean, 1 in about 14 million, that gives you a pretty good idea of what the probability is. Here, this might be, as you start making a bigger number on top, it might be a little harder to read. So here we got 0.0018%. That might be a little easier to comprehend in this case. So these we're definitely using percentages could help versus the decimal. The fractions, though, do give a good view, especially when it's 1 or a small number out of. And then in this last one here, this is really hard to read. These are hard for people to relate. those two sizes. So if we said 13% or 0.13, those are much easier to relate. So that's why it might be a better time to use that. Neither one is right or wrong, just sometimes it makes more sense in terms of readability to use those. So there we have, again, probability. Find the number of combinations that we want, divide it by the number of total possible combinations.